Look at this view of the night sky. It is easy to assume that stars and galaxies float aimlessly in an infinite, empty void. For a long time, astronomy treated the universe exactly like this, a random scattering of independent, isolated islands. But in the early 20th century, observers noticed a glaring mechanical problem. When they measured the speeds of galaxies moving inside massive clusters, the math collapsed. The galaxies were moving far too quickly to be held together by their visible mass. Based on what astronomers could actually see, those galaxies should have flown apart like sparks off a fire. This is astronomer Fritz Zwicky. Standing outside the Palomar Observatory in the 1930s, he identified this exact anomaly. He mathematically proved that some kind of unseen, highly dense mass had to be acting as gravitational glue to keep these galactic clusters intact. The glittering stars we observe are a thin facade. Their movements obey a much larger, completely invisible force. This is the Sloan Digital Sky Survey Telescope in New Mexico. When modern surveys began using instruments like this to plot the exact three-dimensional coordinates of millions of galaxies, they expected to map a fairly even, random distribution of light. Instead, as next-generation observatories, like the segmented golden mirrors of the James Webb Space Telescope, peered deeper into the ancient cosmos, a distinct geometry emerged. The galaxies are highly organized into vast, distinct threads. This 3D map illustrates their finding. 85% of the universe's mass forms a colossal, interconnected dark matter skeleton called the cosmic web. Highlighting where glowing dots intersect these dark filaments reveals a strict dependency. Ordinary matter requires this hidden framework to form galaxies. Every shining star and spiraling galaxy humanity has ever recorded is physically suspended along a sprawling framework we cannot even see. To understand how this massive skeleton took shape, we have to rewind to the very beginning. Immediately following the Big Bang, the newborn universe was incredibly smooth, a dense, nearly uniform fog of ultra-hot particles. This is a photograph of astronomers Arno Penzias and Robert Wilson. In the 1960s, they accidentally detected the cosmic microwave background radiation, which is essentially a fossilized heat map of that ancient, uniform fog. Modeling the early universe as a flat plane reveals minuscule temperature variations. These exaggerated ripples are quantum fluctuations, microscopic density jitters from when the cosmos was smaller than an atom. As space rapidly expanded, these ripples instantly stretched into massive gravitational peaks and valleys. The grandest, most massive structures we observe in the cosmos today are blown-up copies of the universe's smallest, most ancient microscopic uncertainties. Dark matter's gravity collapsed a uniform cloud into vast, interconnected threads. Ordinary hydrogen and helium gas slid down these steep gravitational slopes, gathering directly into the filaments like rainwater. At the geometric intersections, massive pressure sparked enough energy to ignite stars, birthing massive galaxy clusters. Recent studies from the University of California, Riverside prove this relationship goes all the way down to the spin of an individual galaxy. Edge-on-disk galaxies physically align their rotational spins to run perfectly parallel with the invisible filaments feeding them. The cosmic web acts as an active, mechanical dictator. It herds gas, feeds star formation, and strictly controls the physical orientation and survival of every galaxy strung along its threads. This architecture gives us a very specific cosmic address. Earth, the Sun, and our entire Milky Way are merely passengers, suspended on a single dark matter thread deep within the Laniakea supercluster. If you travel past the edges of our local supercluster, you encounter cosmic voids. These are terrifyingly massive stretches of absolute nothingness, tens of millions of light-years across, where gravity has entirely evacuated the matter. Looking at a cross-section of the web, we can see a mysterious opposing force at work. Indicated by these outward-pointing arrows, dark energy is accelerating the expansion of these empty voids. It pushes outward, fighting directly against the inward pull of the web's gravity. As the voids swell in size, that accelerated expansion violently stretches the dark matter filaments. The threads thin out. driving the galaxy clusters further and further apart. The observable universe we live in right now is caught in a fragile, temporary balance. It is locked in a violent tug-of-war between gravitational structure pulling inward and cosmic expansion pushing outward. If we project the cosmic timeline forward, the math points to a clear winner. Dark energy will eventually overpower the Webb's gravitational glue. As this filament stretches under the strain of expansion, it reaches a breaking point. The dark matter threads will snap, permanently severing the gravitational connections between galaxy clusters. Once isolated, those galaxy clusters will be cut off from the flowing supply lines of hydrogen gas. Without fresh raw materials, the birth of new stars will permanently cease, and the nodes will slowly fade to black. Humanity happens to exist in an incredibly lucky, privileged pocket of cosmic time. It is the exact epoch where the Webb is fully woven and its intersections are ablaze with starlight. The glittering night sky we admire is a fleeting arrangement. Those stars are simply the bright, dyed embers of a temporary, invisible skeleton that is slowly pulling itself apart.